Calorimetry. Calorimetry is the technique to actually measure the amount of heat involved in a chemical or physical change. And so, for example, I have a reaction happening. Maybe it's exothermic, so it's releasing heat. How can I measure that? How can I actually measure how much heat is being released? Right. Well, if it's being released, it's very likely to be absorbed by something in its environment, something out there. Right. So, first of all, let's define what that is. We've got the reaction here happening. Heat is coming out of that. This is what we would call the system. The actual thing that we're interested in, that we're looking at, the system, and in this case it's releasing that heat. Everything outside of that system, that is to say everything surrounding it, in this case I'm doing this reaction in some water here, it's in an insulated container here. Even beyond that, if you will, everything out there is called the surroundings. And in this case, again, the water plus the actual calorimeter, the instrument that we use to measure this heat, is the surroundings for that system. And energy, you can't create or destroy it, you can just shuffle it around. Energy has to be absorbed as it's being given off by this reaction. It goes somewhere, in other words. Now in this case, a calorimeter is highly insulated, and so hopefully that energy cannot make it past those insulated walls, or if it does, it's a very small amount and we can neglect that. We can just ignore it. And so the reaction giving off the heat, where does that heat go? It goes to the water that's inside this calorimeter, and probably the water in which this reaction is actually happening. Okay. So an exothermic reaction, that system is going to be giving off the heat. An endothermic reaction, the system is being absorbing the heat. And so if you put yourself in the role of the system, kind of say, okay, I am the reaction. Am I giving that heat off, in which case I'm losing it? I would call that a negative Q. Or in this case, an endothermic reaction, I'm absorbing the heat, I'm gaining it, so I would call that a positive Q. So Q is always from the point of view of the system itself. Now the surroundings would have a positive Q over here in this case, or a negative Q. But when we do this reaction again, you put yourself in the place of whatever it is and say, is the heat increasing or decreasing? Am I giving it off or am I absorbing the heat? That'll tell you whether it's positive or negative. And because it doesn't make it beyond that surroundings, if you will, well, what would be beyond the surroundings? Nothing. Right? So if I add up that, it better equal 0. One of them is losing it, one of them is gaining it, and it's the same amount. So -5 plus 5 has to equal 0. Right. So for example, if we take a look at 3 in your textbook. Oh, I went not far enough at all. Different types of calorimeters they're talking about there. Okay, heat transfer between different substances. All right, 360 gram piece of a steel rod dropped in 425 milliliters of water, 24 degrees Celsius. The final temperature of the water is 42. The rod must have been hot, right? And when it was dropped in the water, it warmed it up. Heat flowed from the rod to the water, and it kept flowing, and it kept flowing until the temperature of the rod and the temperature of the water were the same. Then it stopped flowing. Nowhere else to go. All right, it says calculate what is that initial temperature of the piece of the rod. Now we know it's going to be hot. Right? It's going to warm it up. And it says assume the specific heat of the steel is approximately the same as iron, and we can look that up. So we're going to have to look up the specific heat of iron in the table. And that all heat transfer occurs between the rebar and the water. That is to say, we're not losing any. Again, if these calorimeters are well insulated box, it's not going to make it past that, and so that assumption is a good assumption. All right, so here I wrote down, I summarized, oops, where am I? There it is. I summarized, no, that's not it, 5.3, got it. What's happening, here's my steel rod, my iron rod, it's dropped in, it's 360 grams. I've got a total of 425 milliliters of water inside this calorimeter. I know the water started at 24.0 degrees Celsius, right? And it said it ended up at 42.7 degrees Celsius, so there's my initial and final temperature. They're asking me, what is the initial temperature of the iron? Hey, note that the final temperature of the iron is the same as that for water, 42.7 degrees, because again, that's when they reach thermal equilibrium. All right, I can always always start off these type of equations with, or these type of problems, I'm sorry, with the same equation. Essentially, what's being lost and what's being gained, you add it together, the heat, and it will equal 0. So in this case, the heat that flowed out of the steel plus the heat that flowed into the water, you add that up, it has to be 0. Again, this one's going to be positive and this one's going to be negative by the same amount. Alright, so now let's just expand. What is Q of the steel? Well, it's the specific heat, the mass of it times the specific heat times the change of temperature. That's what Q always equals. And again, that goes back to our definitions right back here of what heat capacity is. Just turning that around and solving it for Q, it's Cm delta T. Okay, so instead of Q, I'm writing Cm delta T right there for the steel. I'm doing the same thing for the water, Cm delta T for the water. Now, of course, the mass of the water is different than the mass of the steel, so I put little S tags or little W tags just meaning steel and water. You can make up your own tags, call them what you want. The heat capacity of the steel, that's a different value than the heat capacity of water. We could look both of those up in the table. The change in temperature of the steel, again, that's a different change. It went down, it dropped by so much. The change in temperature of the water, it went up. And they kept going until they met in the middle, until the temperature was the same. Alright, so you add all that up, it still equals 0. Let's plug some numbers in. The mass of the steel, they told me it was 360 grams. The specific heat of the steel, well, we go back to our table and we look it up. Steel is mostly iron, and iron here, there we go, it's 0.449 joules per gram Celsius. So 0.449, there it is. And the change in temperature. Well, I know the final, remember it's final minus initial always. The final is 42.7, they told me that. The initial, I don't know. That's what I'm asked to solve for, so I'm just going to leave that as Ti. Alright, and what about this one, the water? The mass of the water, well, it was 425 milliliters. Density of water is 1 gram per milliliter, so that's the same thing as 425 grams. If it were a different solvent, you'd have to use that density to figure out the weight of that. Right? But usually we use water, and which is convenient because that's just a 1 for its density. 4.124 joules per gram Celsius, that is the specific heat of water. We saw that before, but just to remind you, we scroll back up here. There's water. I look it over here. Yep, its specific heat is 4.184. And the change in temperature of the water, again, final minus initial, we know both of those. Right? And that whole thing, of course, has to equal 0. Go ahead and put that down here, equals 0. Now we just need to solve this for Ti, the last one. So you can multiply this all out, multiply this out, add, subtract. That's just algebra. I'm not going to show you the details. You should know how to do algebra at this point. It comes out to be 248. So the initial temperature of that bar, pretty darn hot, 248 degrees Celsius. Of course, it dropped all the way down to 42, so it had a change of over 200 degrees that it cooled off. And this water that we dropped it into, it only went up, what is that, 18 degrees? From 24 up to 42, something like that? Yeah, 18 degrees. 19 degrees because 0.7-ish. How did the water only go up that much when the steel cooled down that much? When, look at the mass of the steel was just a little bit less than the mass of the water. Well, that goes back to the huge difference in specific heat. Remember, water is pretty darn high, 4.184, whereas the steel was only 0.4. So the water, again, can hold a lot of energy without increasing its temperature so much. And this is a great example of this problem of how that's true. Okay, let's try example 5.5. Go to the book here. Example 5.5. Example 4, same kind of a thing. Q equals Q. Okay, 5.5 though. Here's what I want to look at now. 50 milliliters of 1 molar HCl solution, hydrochloric acid, in water. There's its concentration, 1 mole per liter. And 50 milliliters of a 1 molar sodium hydroxide solution. Alright, so again, 1 mole per liter. We're going to mix them together. 22 degrees is my initial temperature. They're added to a coffee cup calorimeter. What is that? That's simply a styrofoam coffee cup, maybe 2 of them put together. That's my insulated box. So it's a calorimeter, just like any of the other ones are. Right? The temperatures reaches a maximum of 28.9. Now how is that? They were both at 22 degrees. I mix them together. All of a sudden they go up to 28.9 degrees. Why did they get hot? Well, it's because I've got acid, hydrochloric acid, being mixed with a base, strong base, sodium hydroxide. So I get a neutralization reaction when they mix. Here's my acid plus my base. As always, neutralization reactions, I'm going to get a salt and water. Right? This is a reaction occurring, and as we know, many reactions involve energy. Either the release of energy if it's exothermic or the absorption if it's endothermic. The fact that this reaction made the temperature go up for the water that's in tells me that that reaction was exothermic. It released that energy, the water absorbed it, and its temperature went up, of course. All right, so I can see now, all right, I see why it went up, and the coffee cup calorimeter is trapping that heat in there. It's not letting it go beyond that, and so all of that energy from that reaction went into the water, causing its temperature to go up. Now, what is it asking us? It's saying, what is the approximate amount of heat produced by that reaction? Okay, so 50 milliliters of 0.1 molar hydrochloric acid, 50 milliliters of 0.1 molar sodium hydroxide. Again, initial temperature is 22, final is 28.9. The reaction heat plus the water heat will add up to 0. Again, all these problems you're going to start off that way, because one of them is going to be positive and one of them is going to be negative. In this case, the heat for the water is positive because it absorbed the energy. That's why its temperature went up. The heat of the reaction is negative. That seems counterintuitive at first, but if you are the reaction and you're producing heat, that is to say, you're giving it off, you're releasing it, well then you're losing that heat and it's negative for you. So Q reaction is negative, Q of water is positive. When we add them up, we get 0. Now we just need to fill it out. Q of the reaction, I really don't know. I can't expand that anyway. This is not like a substance. This is a reaction happening and it just gives off the heat. So just leave that as Q. However, Q of water, I know that's Cm delta T for the water, and that should equal 0. Now I can plug in my numbers. I know specific heat of water is 4.184. The mass of the water, 100 grams. We said it was given in 100 milliliters, right? 50 here, 50 here. That's a grand total of 100. So it's 100 grams of water. Temperature final minus temperature initial. That's how much it went up. Plug it all in. That equals 0, right? Plug it all in. Solve for Q. Q equals 2,890 joules is the unit because all the other units have canceled, just like before. Or 2.89 kilojoules is another way to say that. Alright, so that's how most calorimetry problems work. You've got something that's releasing the heat, something that's absorbing the heat. If it's an endothermic reaction, its Q is going to be positive. The Q for the water would be negative, and actually the water would get colder. Because again, the water was losing the heat and giving it to the reaction. The reaction was sucking it up, if you will, absorbing it from its surroundings, which is the water.